Well, um, just us at the moment, but I'm gonna start recording here. So yeah, my plan was to kind of talk about the start with the assignment three, see if anybody wanted to ask any questions about it. So bring that up first. Most of the rest of today, I was going to go over the regularization, talk about that. So that was kind of the rest of the assignment three. But was there anything that you're wondering about on the assignment so far? I've had a couple questions about. I know one of the regularization. I can't remember which one it is, lasso or the ridge, but the default, if you it, you have to have like a really small amount of regularization on it to get good results. But then when you have a small amount of regularization, you get convergence errors. That seems to be normal right now. I know, like probably everybody will run across that. So yeah, if you do the if you do it the way that it's described, and you try different values of alpha to regularize, I think it's is it the ridge? Anyway, one of the two. You'll find that you have to make it kind of pretty small, but then when you get it pretty small, or actually for a lot of the range of alpha, it'll end up giving you convergence errors. So I'm not 100% certain what it's doing there. In fact, I should probably investigate that more. So you would think that if you had zero alpha, you should basically just get a regular linear regression, because you're basically saying don't use any regularization. But yeah, you don't get exactly the same results as you would as you do for just doing a straight up linear regression. So I'm not certain exactly what that model is doing for ridge there, nor am I completely certain why it gets. I mean, it makes a little bit of sense to get the convergence warnings, because basically what you're doing is you're saying that I want just to have a little bit of regularization, and that makes it tough for it to find good fitting parameters. So it can't find anything that's both has where the parameters are being kept down a little bit, but still working well as a model. So, but anyway, so yeah, anybody watching this after the fact, I have had at least 2 or 3 people already come up against that. So it is normal to get that. You don't have to worry about that too much. So I think I discussed it in the assignment. Let me just check that real quickly. Maybe not. So yeah, if you do get regularization errors, which convergence errors on one of those, that does happen. That's kind of normal. So usually you kind of want to, you certainly, kind of a general thing on this for anybody watching. I mean, whenever you get warnings, you shouldn't just ignore them. So warnings, won't stop the cell from running, and you can keep doing stuff with whatever happens, but warnings are usually there for a purpose. So a lot of the times, you really should fix wherever the warning is. So a lot of the warnings that we'll run across in this class are things that they've changed the user interface for a little bit. So it's a good idea to fix them now, so that if you're still using that notebook later on, once the version updates, it'll still work. So usually those kinds of warnings, you want to right away try and do whatever it's saying in order to do it the new way, so that your stuff keeps working. So yeah, I was gonna we'll get into talking about regularization, what that means, but I don't think, so the last Tuesday, I had some problems with the recording last Tuesday. I was just checking here, so I think that we're working today, hopefully. So I'm not certain what happened. But last time we I only brought up the actual assignment right at the very end for just a little bit. So we spent last time talking about the learning curves and underfitting and overfitting. So that's really kind of up through task 4. So task 1 is just loading the data. And you are supposed to plot it, so make certain that you do visualize that like is shown. That should just be a basic scatter plot there, but I mean, you should use a scatter plot. You don't. This is just made up data, so you don't really have any units, or it's really just you've got one feature X and you've got a value Y that we're going to try to fit a regression model to. So fit a model that's an actual real valued predictor. So kind of like we talked about on Tuesday, you should start by the model. I'm sure it's discussed in here. The secret function that generates that data is probably something like a degree 6, 7, 8 polynomial, something in that area. Just to give you some kind of hints about what it's doing. So kind of the ultimate goal of the assignment is to estimate the parameters for all of the. There's only one feature, so we've got the x to the 0, x to the 1, x to the 2, up to some x to the n power on the secret function with a little bit of noise added to it that you're trying to fit a polynomial regression to. So yeah, you're supposed to start with an underfit model. So like we talked about, the main goal of this is to, so you should just fit a line, a degree 1 model on this one, like it says here. Degree 2 polynomial. So the main thing that this will give you, though, this will give you some idea that this should converge. When you have an underfit model, that gives you kind of that gives you kind of an upper bound, right? So whatever the performance that this converges at, you know that. You shouldn't be satisfied with a more complex model that's not getting much of an improvement on the root mean squared error. So on the error measure that you're using for your regression model. So if you've got a model that's obviously underfitting, you can use it for comparison. But if you're trying to make better models and they're not doing any better than your underfit model, they're not doing good, right? They're not doing anything. So that's the main purpose of an underfit model. But that's often a starting point when you're building, when you're trying to model some data as a regression that you haven't seen before, or any kind of supervised learning. So all the stuff we do here also applies if we're doing a classification as well. So you might want to start with an underfit model, or you want to start with some baseline model that's just guessing. That gives you kind of a basic idea of what performance you can expect, and then when you start trying to improve things, you'll want to have something that does better than your baseline or your obviously underfitting model. So, but yeah, you should see that it does converge here. Actually, I guess you won't really see that until you do the learning curve. So the learning curves, this is. I gave a lot of this, so anybody that goes through the notebooks from my lectures, this is mostly there. We changed the format a little bit. So basically, the function that you're supposed to do in this assignment is not supposed to actually do the plotting. It's just supposed to calculate the error, the error on the trained data and the error on the test data for. When you train it with just one sample or two samples up to some number of samples, right? And then you're supposed to take that data and plot it. So for all the rest of these, you'll be reusing your learning curve error function, but then you should take the resulting stuff that comes back and give learning curve plots like we did in our lecture notebooks. So for this one is supposed to be returning back, basically two vectors. So one of train errors and one of test errors. Another thing about this, I had more than one person already ask about this as well. This is expecting that the, so for the tests on this one, this is expecting that the random seed is set before you call the function. So I think that you won't pass the tests if you set the random seed inside of the function, or especially there's methods, for example, when you, so you do have to split the data that's passed into a test and what we're calling like a validation set. So hold back some stuff to check the errors on data that was definitely not ever trained with when you produce these learning curves here. So, but yeah, when you do that split, you can specify a seed, but you'll end up not being able to pass these tests if you do it that way. So you really shouldn't be setting a random seed inside this. You should just be expecting that the random seed is set before, immediately before any other thing is done to generate random numbers, and before the function is called. Right. So yeah, in the test, you'll see that we just create one made-up data set, not the same data set that you're using. So in this case, some people in past assignments have kind of ignored the input parameters sometime. So yeah, these tests definitely wouldn't work for that because we're not using the data, that secret function. We're just generating some random data here. So setting a seed, generating some random data, and then expecting that if you do the learning curves the way it's described, you should get these exact numbers coming out on the train errors and the test errors, or the validation errors. So I guess I should be consistent. Yeah, well, we call them the test errors here. So I hope that doesn't confuse people. So later on, at times you actually have to split your set up into three different things. A train, a validation, and a test set. So the usual convention is that the test set is held back for the very last one evaluation of the final model that you do. But if you're building multiple models and comparing them, usually you'll train them on the training data, but you'll evaluate them on the validation data when you're comparing the performance of different separate models. And then the model that you pick, if you want to get a final estimate of its performance, so you would do that on that final last test data, usually just once. So we'll probably talk more about that later. In a later assignment, we'll need to split up stuff into three parts to kind of do it right. So the issue is that information can leak in. So when you're tuning multiple models, you're going to be kind of tuning it to do well on that validation data or whatever data you're using to compare the performance between them. So sometimes you'll find that you might end up with a model that ends up doing badly then when you do it on some final test data that you never use when you were trying to tune stuff. So it's kind of like a final sanity check that I haven't done something that leaked in information and my performance collapses on what I thought was going to be my final model, but it starts doing really bad on data that I wasn't kind of using when I was tuning stuff. So you'll see that train validation test split in other places. But yeah, I should probably be more consistent on my terminology there. I called it validation in some places, and we called it test errors and, in some other places as well on this assignment. And then Yeah, so we'll talk about some regularization here in a second, but then we also ask you to do an overfit model using a degree 100 polynomial. So as some hints that's much that's way overpowered. The actual degree of the secret function is only 8 or 7 or something like that in that area. So if you fit it with a degree 100, you should expect it to overfit if you're not doing anything to try to fight that overfitting. And in fact, that will happen if you do it the way it's described here. So like we showed in the previous lecture, or if you looked at some of the examples in the lecture notebooks for this week, what that looks like for a regression model is a very overpowered model will wiggle around a lot and try and go through every point that you're training it with. And so it'll do well on the error function. So on your cost function, it'll look like it's doing well, but it'll collapse basically. It won't be able to do predictions at all on data it wasn't trained with. It'll get really bad performance if it's badly overfitting. So this model should mostly be badly overfitting. Again, summarizing kind of the stuff that we talked about last time, what you should see on that is you won't see convergence. So when a model is overfitting, the evaluations on test data or validation data do poorly. They never do as well. They do much worse than the error cost function on the data it was trained with. So they never kind of come together. They never converge if you look at the learning curve. So that's kind of the signature of a function that's overfitting. But the one piece of information you can get from overfitting, though, is that the performance that you see on the data that you train with for an overfit model, so the error or the cost that you converge on for the data being trained with, is a good target. That ends up being kind of a lower bound of what you might be able to do. So you probably will never be able to get a model that can quite do that well on data it wasn't trained with, but that's ends up being kind of a goal. So you wouldn't be able to do better than that. So you can't do any better than overfitting, highly overfitting in terms of your cost. But a good model that's a Goldilocks model that's not underfit, not overfit. It's about the right power for the data you're trying to model. Will approach the performance on the cost function or the error function that you can get for the overfit model that it does on the data it was trained with, right? So this gives you some information. This gives you a target of what you want to try to achieve if you're doing regression. All right, so there's a purpose for that. And I had some people ask, it's mentioned in here that you should before you do these learning curves, hopefully, I'm sure it's mentioned, you should be setting the seed before you call the function to do the learning curves. So it should be set to 42. I guess, when we do the tests, we will set the seed for you. Before you do your learning curves, it might be a good idea to set the seed before you call the function that gives you the learning curves to something like 42. Yeah, we do mention that, so at some places anyway. So. Another thing that's mentioned that some people don't understand, I showed this, maybe when I go back to the lecture notebooks later on, I'll show this, but the goal is we're trying to visualize the resulting learning curves here, so there's information to be gained from these plots, these learning curve plots. And the information is really kind of the level of the cost or the error function. So, for some of these curves, when you do them, the cost on the validation data especially will be really high in some places. If it doesn't converge, it might be really high for the whole range of the numbers you're plotting. But even if it's converging at the beginning, it might be really high. So if you don't limit your y-axis, everything will be squashed out or look like everything's down to 0, and you can't really read what the results are. So yeah, you do need to limit the y-axis so that you get the information that's trying to be conveyed by doing, by fitting the underfit and the overfit model and plotting these learning curves. You're trying to learn. You're trying to really get like an upper and lower bounds of what is possible when you're fitting regression models to this set of data here. Okay, and then, so I'm going to jump and talk about regularization. So there's other ways to fit, to fight overfitting, and that's what the other notebook for this unit was about. Was really about fighting overfitting, right? So in machine learning, it's easy to use a powerful algorithm that will be able to overfit the data set that you have. So you have to be able to detect that, and you have to use different methods. Regularization is one of those methods that you can then try to use to tune your model so that it will do well at predicting on data that it wasn't trained with. Okay? So we look at basic regularization, and we look at there's two basic types. So statisticians call those lasso and ridge. These are the L0 and L1 type of regularization here. And then, don't skip over the, do fill out this table. I am expecting this and a little bit of a discussion here. So it probably should be at least a bit of a paragraph. So you should kind of describe your underfit and overfit model and a little bit of the things that you did, the different alphas that you tried, and what your observations were when you do the regularization with the lasso and the ridge. So I see, and you should be using Markdown, so you should be filling out like this table and putting your discussion here, since this is supposed to be written in English. So do use Markdown, fill out the table. So the idea on the table is to kind of try and show some bounds at least. So lasso that was too small, so an alpha that was too small or an alpha that was too big. But then something that was that seemed to be about right, so that you were actually fighting the overfitting with using lasso regression, the same with ridge regression. So, although don't sweat this too much. So especially for one of these, a good alpha is really pretty small. So basically, having not very much regularization at all ends up being if I remember right, being kind of the one that works the best. So, I think you'll probably find that out if you try some things. All right, but yeah, I will look at that, and you'll lose like 5 or 10 points if you don't give me the discussion and stuff here that I'm asking for, the written part here. And then finally, so you should try and do this by hand, just basically trying different values of alpha, different amounts of regularization in order to try to find a model that seems to be performing well, that's fighting the overfitting well. So you'll know that you're fighting the overfitting well when you're getting an error that's approaching the cost of your overfit model that it did on the data it trained with, but you're getting that performance on your held back data that it wasn't trained with. But yeah, if you do it by hand, the scikit-learn, I probably won't have a chance to talk about today, but there's some examples of using what are known as grid searches. So you can do this more systematically using the scikit-learn library. So basically, instead of trying different values of alpha by hand, you can say try all the different alphas in a range from 0 to 2. So try like maybe do all the values like 100 evenly spaced values or 100 values spaced logarithmically over some range. Anyway, that's kind of what's being asked for you to do there. There's an example of doing this. So really, in this case, since our secret function is really changing the degree, so you don't have to do anything at the end here except for just uncomment these. But this will be an example of, since we know that really the secret sauce here is that the degree of the polynomial that was used in the secret function will give you the best model if you can exactly match the right degree. There's an example of systematically searching degrees from 2 to 100 and using that to figure out which ends up giving you the best. Here on the grid search, you have to tell what the parameters you want to score by, and so it will check the parameters that you specify here. And you can do something in order to get like what it figured out was the best one by the measure you asked for. So we're using the negative mean squared error here. So the mean squared error is the root mean squared error, although it's not using the root, it's just using the regular mean squared error. But the reason why you use the negative is we have to think of these problems in terms of a minimization problem. So the optimization techniques that are used for this, it expects that the cost function is a minimum function, so that it's trying to find the minimum cost. And the mean squared error is oh no, wait a minute. Well, yeah. So anyway, you should just use that. I have to remember about the acid, so that's not quite right. It's already a minimum function when you use the mean squared error. So now, kind of can't remember exactly what's the negative, but yeah, that's what you should be using for the grid search here. Oh yeah, just the opposite. So it needs to use a maximization function. I can't remember why. So that's why we have to use the negative. So the mean squared error is a minimization function, so you want the minimum cost when you're using mean squared error, the root mean squared error, but it's expecting a function where the higher your error function is, the better. So it's really expecting something that it maximizes instead of minimizes. Now, I don't know the technical details of why it does that, but if you just take the negative of a minimization function, that's usually enough in order to change it into a maximization. So it's really the same thing. You're just inverting the sense of which direction you want to search for them. All right, but this is really useful. In fact, this yeah, I'd meant to kind of mention about the final project for the class as well. So kind of just a reminder about it. I'll probably usually try and mention that at least every week that we have remaining for the class here. So it's a good idea to try and work on that a little bit every week. I recommend everybody try and do something and make at least one commit each week on the final project. So that'll help you keep it in your mind, keep you making progress moving forward on it. So yeah, I don't remember if I said this on Tuesday, but I would recommend a goal for this week, since you were supposed to have chosen the data set you were working on, that you at least get the data set into the data subdirectory if you didn't do that already. So if you have something small enough as like a CSV file, you should get that data in there, or create some sort of a function that will automate the process of downloading that data, so that it just does like a download to get the data from a URL and puts in the data subdirectory. And maybe also create your first notebook. So create a IPython notebook that reads the data in at least, and you have a start for doing your actual data exploration, so that you've got the data read in and you can see what features you have, what columns you have, and how many samples you have, and can maybe start exploring the data. So that would be a good goal for this week, and make a commit of that work, right? So I will probably have at least a little bit of the points on the final project will be towards, did you show me that you were making regular progress? So were you making regular commits weekly? Doing things, so I get an idea that you were actually doing it. You didn't just have the project that you copied from somewhere else and did it all in 1 hour on the last finals week. You look like you were actually really, working on the data yourself and doing stuff regularly to make progress on it and think about it. I started on that digression a little bit because a good thing later on, once you get to thinking about building some different models for the data set you're working with and comparing them, grid searches are good tools. So, if you're trying to tune a particular model, or even you can also use this in general to have a couple of different models and tune them over a range of parameters, and then so you can compare them and see how they do against one another and how they do as you vary different meta parameters, like the amount of regularization or other stuff. Okay, so yeah, that was the main stuff I wanted to mention about this. This is the last meeting that we had before it's due, so I am looking for these by Friday. I know, I think last time I looked, at least almost everybody had accepted the assignment sometime when I looked last on Tuesday or something, I think. But yeah, make certain you get that in. Try and get that in by Friday. I'll probably be looking at that this weekend. Okay, so let's switch over. Talk about regularization. Some of the details here. It's our last thing. So. Okay, so just real quickly on the learning curves, just to mention, so, for the people that were asking, if you watch this, or if you were wondering about what we're talking about, yeah, you usually do have to limit these, because the basic idea is that your validation error especially will be really high at some point. So if you don't do that, everything will be squashed down. You can't really read the level that you end up at on these your train and your test errors, or here's what I was calling it, train and validation, I guess, in the lecture notebooks. So, all right. So So we've already, got the background that you need to understand regularization. I already mentioned it today. So the idea is that it's easy to build overfit models. And in fact, you often want to do that as like a first step before you start tuning things. So that will give you an idea of what you might be able to achieve. So the idea is how do you fight overfitting? So how do you do something so that you have a model that's still powerful enough to do well on the data, but won't overfit, won't learn the noise in the data, will still do well on unseen data it wasn't trained with. So one way is to basically just add a penalty. So regularization is about the reason why things are overfit is, remember, we've got multiple parameters. So in this formalization here, we're calling those theta. And we've got n of those. So if I've got n features, I've got n of these theta parameters. We exclude 0 here. So by convention, this formalization, 0 is usually going to be the parameter for the constant term. So raised to the power of 0 here when we're doing the polynomial regression. Okay. So that corresponds to the intercept term here. So we only do this on the terms that aren't for that constant one, but that correspond to the n features that we have in the data set here. Right? So for polynomial regression, these correspond to the x to the 1, x to the squared, x cubed, and so on. But for any other data set, you normally have more than one feature. So those just correspond to feature 1, feature 2, feature 3, feature n. So the idea for what's being done for regularization is if you're overfitting, you can end up with really high values for the theta, saying that give a lot of importance to this feature 1 or feature 2 or whatever it is. I end up with a really high value, in terms of like the importance of that feature is for doing my prediction. Right? So if you just add in a penalty, so that here what we're doing is we're taking the same mean squared error function that we talked about last time that we developed, right? But to that we also add in the summation of these just the features themselves. Right? So remember, the mean squared error is really the difference between for a particular set of theta, our parameters, mean squared error is measuring the difference between the predictions I'm making and the true labels, and taking the square of those and summing those up, and then the average. So that's the mean of the squared of the errors there. So here, all we're doing then is we're adding in the summing up the errors themselves and adding that into our cost function, right? So the cost function becomes not just the mean squared errors, but the combination of the mean squared errors plus, I think of this as a penalty term. The regularization penalty, right? So basically, and the reason we could use actually the two types that we'll use for ridge and lasso. The difference is for the ridge we square the term, and for the lasso, what's happening to my? For the lasso, we just take the absolute value. Okay. So mathematicians call this doing an L1 regularization. And they call this doing an L2 regularization. So that's another term you might hear. So a lot of these techniques were kind of arrived at in separate disciplines. So they have kind of different nomenclature and definitions and formalizations. So statisticians called this ridge and regression, and mathematicians use this idea of L1 and L2 norms from linear algebra is another way that you can formalize doing this here. So we do have to, again, these theta parameters can be positive or negative. So it could be multiplying. So in order to have, if a parameter is negatively correlated with what you're trying to predict, you would want to actually have take the negative of it. Because if that parameter is big, what you're trying to predict is going to be small. It's going to be in the opposite direction, right? So these parameters of your model need to be able to be negative or positive when we're doing a regression or a classification. But if you sum that up, then your penalty could just end up being zero. They could cancel each other out, right? So when we're doing this penalty for regularization, we really want the magnitude. So how big they are, or how close they are to zero. So that's why we take the square or the absolute value. So what we end up with is a summation of, for this penalty term, of how far away from zero they are, right? And what this is saying intuitively for regularization is I want something that is both good at predicting, at minimizing the error, right? So my ultimate goal is I need something as close to zero as possible. We're thinking of this as a minimization problem here, right? So that the cost is good when the errors are zero, or as close to zero as I can get. But the penalty term is going to be good when the parameters are close to zero, right? So by combining these, what we're saying is I want a model that minimizes errors, but also does that with as small parameters as possible, as close to zero, right? So it ends up being a balance. I mean, if they were all zero, obviously the model wouldn't be able to make any predictions, so you'd get bad cost. But if they're all really high, though, that can lead to overfitting, right? So if this term gets really high, you're much more likely to be overfitting the data for various reasons, right? So, and that's where alpha comes in. That's what you're varying for this assignment, both for ridge and lasso. So if alpha is zero, you're not using this, you're just doing regular linear regression. But if the bigger alpha is, the more importance you put to the regularization penalty. So if you make it really big, you're going to be basically driving the parameters to get towards zero. All right. If you make it too big, all the parameters will become zero. So you'll just be ignoring that you're not doing well on reducing the errors. Right? Your goal is just to have a model where the parameters are small or zero. If alpha is too big. So that's what you're supposed to be doing for those two steps on this assignment. So when alpha is too big, you're going to be kind of ignoring the errors, and you'll be overfitting. If alpha is too small, so I'm sorry, you won't be over. So if alpha is too big, you'll be driving everything to zero, and you'll get a model that's underfitting. Right? So when alpha is too big, you ignore the errors, but you'll be reducing kind of the power of your model conceptually, so you'll end up with something that will be closer to performance of like an underfit model. But if alpha is too small, it would be like an overfit model. And by tuning that, you should be able to find, usually, not always, but usually you'll be able to find something of a range where you get something where it balances. So you keep it from overfitting, but you're still getting a model that does well on the cost function, right? And when you do that, it'll do well not only on the data it was trained with, but it'll perform well on unseen data, on test or validation data. So yeah, if you haven't looked at these, these are meant to give you an intuitive feel of how this is working, right? So here you're doing similar things to what we're asking you to do on the assignment 3. So we've got the same idea. We've got a function, which is we were using the same one as we did before, so it was like just a quadratic function. So here, when we're using the ridge regression, we're trying different values of alpha. We have one model that we set alpha to 0, so this gives you basically a regular linear regression. We're not using any regularization. When alpha is 0 here for a ridge model. And in this case, an alpha of 1 gives you kind of a good balance, or we have an example of where alpha is really big, of 100 here. Right. So you can see the effect on, again, you wouldn't normally know this if you're working with real data, but the true function is the dashed line here. So when alpha is too small, we're not doing any regularization. And I skipped over, but yeah, we were using the same kind of thing. We're using a degree 25 model where the true function is a degree 2, so an overpowered polynomial regression here. So we're getting some overfitting, so it's wiggling around a lot, trying to get into some of the points. So it's modeling some of the noise when we don't have any regularization. The model overfits. But if we go too high, we basically just get a line. It'll be even more pronounced for the lasso here. But really what's happening is we're driving it to, we only have the constant term. Everything, all the other parameters are kind of driven close to 0 here in this case. So, but if you get a good balance, you'll end up with something that even though it's a degree 25 polynomial, it fights that overfitting, so it looks like a smooth function, and it's getting close to the same sort of shape, at least in the range that we're testing it over of the true function that we're trying to fit here. Right. So for ridge regression, because of the way that the square works, so our true function was this, 1/2 of the x squared and 3/4, and then 3 for the constant term. So if you look at this for 0, we end up with just the constant term, and everything else ends up being really big because we are overfitting. We're not doing any regularization here, right? So we end up with some really big values for our parameter, big negatives and big positives in a lot of these places. When we make it too big, everything gets close to 0, right? So you notice everything's really small. So one difference between using the square versus the absolute value is it's discussed in our textbook, but the tendency for the other type, using the absolute value, it will tend to drive as many parameters as possible to exactly 0. Ridge regression, when you're using the square, doesn't do that. So you'll get everything small, but nothing exactly down to 0. So if we are doing something like polynomial regression, lasso can be especially effective because it will allow us to approximate, be able to see how many of the terms that we need. Do we need the square, the cube, or the 4th power to be a good model if you get your alpha in the right range here. So here, this was the alpha that was doing relatively well, so you can compare that to the true values of 3 and 1/2 and 3/4 here, so not quite, but and we still got some other stuff being added in for the higher powers here for our ridge. And in this notebook, the same thing. We do it for the lasso. So yeah, this is the one where lasso is the one where you'll probably get convergence errors. So whenever you have alpha too small in lasso, you tend to get those, and I don't 100% exactly know what it's doing. What I would expect is that again with zero here, it should be doing no regularization, and you should get the same result as if you were just doing a straightforward linear regression. But yeah, if you compare it, it still seems to be doing something. So I don't know exactly what the difference is for lasso here from what we discussed in the textbook. But yeah, we would expect with a zero alpha here that's just not doing any regularization. So it should just be doing a straightforward regression using the mean squared error here. But anyway, you get a similar kind of result. So we have an overpowered model. We're not using any regression, any regularization here, so it should be a straightforward regression. In this case, for lasso, I think you'll get a similar thing, same thing for our assignment. It works. The best value is really still pretty small, so not very much regularization. So once you get above 1 or so, it's too big. And you can see the results of those here, though. So for 1, we're doing too much regularization. So here it drives all the parameters actually to 0 once it gets too big for lasso. So using the absolute value, the result looks like that. Unlike for the squares, everything actually will get driven completely to 0. So you only end up with the constant term. And that's why we end up with a line when it's too big. We're just completely ignoring the errors, and this is the line that is basically in the average of the y, the average value of the thing we're trying to predict. But yeah, so for alpha for 0, I don't know how much to kind of trust this, as it doesn't really converge, but you can see it's still a little bit wiggly. So it's probably overfitting. But still, relatively small values of alpha will get you relatively good performance on the cost on this example here. So, and again, if you look at the parameters for the one that's just right, the Goldilocks that we chose, the 0.01 there, we get 3 1/2 and 3/4. And so yeah, I don't remember why. So I would expect that to be more like 3/4 instead of it was more like 1/4. Maybe I had the model wrong. Have to check again what we did to generate that. Yeah, it should be 3/4, I think. So I'm not certain, but. Yeah, and then I mean, you can combine those. So elastic net, I didn't ask you to do that on the assignment, but elastic net is, I don't know how useful this is, but if you ever have a case where you want to try both of them at the same time, elastic is doing the L1 and the L2, or the lasso and the ridge. Alpha controls the same thing as we talked about before for both of those, but then the R parameter controls the amount of whether I want to do the ridge and 1 minus, since we do 1 minus R. So if R is 1, we're doing all this. We're doing all the second one we talked about, and if R is 0, we're doing all the first one using the squares. So by changing, oh yeah, in scikit-learn, it doesn't use R. You have to use the L1 ratio. But this is another thing I usually mention when I remember this. So this is another reason why it is good to at least be familiar with the formalizations and what's going on, because some of that leaks out sometimes into the user interface, right? So you might scratch your, why is that called L1 ratio if you run across this and read the documentation. But yeah, if you know that, in some circles these are called L1 and L2, regularization. So L2 is the ridge, and L1 is the lasso type. This is the name's coming from. That's how much L2 or L1, or how much of the lasso versus the ridge we want to combine together for this elastic net. Okay, kind of as a final thing here, there's other ways. In fact, really the most common, especially like if you're doing neural networks and stuff, to fight overfitting is just to use early stopping. Okay, so this is another example. This is how the types of learning curves that I'm more familiar with. So what you do if you take my neural networks course normally is you have to train a network for multiple epochs. Because when you're doing gradient descent, if you just train it for one cycle, it won't get down to the minimum. It'll take many iterations of gradient descent to get there. So that's really what we're doing here is multiple iterations of like a gradient descent or an optimization. But you'll get the same kind of result like we talked about for the learning curves, the way we did it in a slightly different way on this assignment. So if you look at the performance of on the data that you're training with, compare that onto held back validation data, what typically happens for many of these models when you are using an optimization like gradient descent is they will improve to some point, and then they will start overfitting. So you'll get to some place where the parameters are just right, and then if you keep going, you'll reduce your cost on the data you're training with, but you're actually beginning to learn the noise. Right? So in these type of learning curves where you're looking at iterations of an optimization, you can just monitor the performance on your held back test or validation data. And if you just keep your if you know what the parameters are, once you detect that you're no longer improving on your validation or your test data, you can just stop there and use those parameters. Those will give you the best performance on predicting test data. This is very common to use these types of learning curves, especially when you're doing neural networks and some other kind of optimization techniques on machine learning algorithms like these. All right. Yeah. So, so that's we're up out of time here for today, I guess. Any stuff that you need to know about assignment 3, let me know. But yeah, that's it. So, I was going to mention maybe a last thing. So we've got next week. We're going to be doing our midterm test. Okay? So next week is all about doing some review of the stuff we've looked at this week. So I haven't brought up the test yet, but we will talk about it on Tuesday and do a review. The test will be open on like Thursday and Friday. So next week is the week before spring break. So I usually try to get in our midterm before we go away for the spring break. So. All right. Yep. That's it. We'll go ahead and end the recording there. Let you guys go.